press rating is not enough to define a working aluminum extrusion line. The real risk is buying capacity that looks correct on paper but cannot hold the profile mix, thermal behavior, handling demands, and downstream quality the plant actually needs. That is why the starting point is the operating requirement, not the largest available machine. A credible 25 millinewtons, 55 millinewtons, or 125 millinewtons decision has to be tied to the alloy family, cross-section geometry, wall thickness, circumscribed circle range, die complexity, shift pattern, target output, finishing route, and the quality characteristics customers inspect. Architectural, solar, transportation, industrial, and specialty programs can place very different demands on force, heat balance, and material flow. The task is to define a representative product mix, including the profiles that create constraints, not just the easiest parts of the portfolio. Expansion potential should be documented as an option, not used to oversize every module from the start. A larger press changes the burden on billet logistics, thermal capacity, cooling, material handling, floor loading, electrical distribution, and maintenance access. The line needs to show what is sized for present production, what is prepared for a future phase, and what must change before that future phase can operate safely and consistently. Once the production envelope is written, the capacity decision becomes a system question. The press must work with upstream billet condition and with the downstream ability to cool, pull, stretch, cut, age, stack, and route profiles without creating a new bottleneck. The right configuration is the one that can produce repeatable profiles at the required rhythm while protecting quality, maintenance access, and future change options. That logic applies just as much to the connected modules around the press. Upstream equipment is not only a list of machines. It is the sequence that prepares a billet so it arrives clean, correctly positioned, and within the intended thermal window. Storage and loading, brushing, furnaces, hot shears, hot saws, manipulators, and controls all have to work together. If the sequence breaks down, the press input becomes unstable even when the press itself is mechanically sound. Temperature consistency is a production control variable, not just an energy issue. It affects material flow, extrusion behavior, surface condition, and the stability of subsequent operations. Buyers need to know how temperature is controlled, where sensing takes place, how transfer delays are handled, and what evidence will be reviewed after commissioning if the billet condition moves out of range. Downstream equipment carries the same weight. Cooling, pullers, stretchers, cooling tables, cut-to-length tables, stackers, aging ovens, and logistics must act as a coordinated chain. A fast press is not an advantage if profiles wait for cooling, lose straightness, are marked during handling, or build up in an uncontrolled queue before cutting and stacking. Thin, long, complex, or surface-sensitive profiles may need a very different downstream response from shorter, more robust products. The strongest specification is built around interfaces, not isolated machine claims. It should show how data, material, alarms, and safe stops pass from one module to the next, who supplies each interface, who commissions it, and who owns a fault after handover. That same discipline should extend to layout, automation, utilities, maintenance access, and future expansion boundaries, so the factory can verify what will work now and what would have to change later. A defensible extrusion line investment record keeps those assumptions visible. It preserves the operating requirement, the module boundaries, the interfaces outside scope, and the criteria for successful handover. That is the difference between a press purchase and a line that can run predictably.